Hello, welcome to your video on chi-square distributions and chi-square tests. So the interesting thing about what we've been doing is we've been using normal curves and actually other curves that kind of look like normal curves that are called t-distributions. And all those are kind of a bell curve kind of shape. Now we're going to start talking about a chi-square distribution that kind of looks like this thing right here. And this is actually a photograph of a shirt that I have that's called Chi-Squaretops because he looks like a Triceratops and it's adorable. But anyways, we're going to be talking about chi-square distributions and chi-squared tests. Now, why do we use chi-squared in the first place? We use it for testing categorical or qualitative data. Everything we've done up to this point has been numerical data. We've been finding mean, median, and mode, confidence intervals, t-values, looking at the mean of one set to the mean of the other set. Well, what if I don't ask somebody a quantitative question and I ask them a qualitative question? What is your gender? How do you feel? Do you agree or disagree with this? Can you respond to this Likert statement? Okay, those are technically all qualitative responses. And sometimes I want to know, based on those qualitative responses, is there like a group preference to something? Or if you're a man, does it mean you respond differently than if you're a woman? Or if you've been at the company less than 5 years, do you respond differently if you've been at the company 10 years or 20 years? All these types of things where we can group people into categories. Okay, that's what chi-squared is about. Implying a group preference, whether data is uniform or not uniform, that's what chi-squared can be used for, okay? So if we want to analyze a potential group preference, it's when we want to look at categorical responses and see, is the data uniform or does it lean one way or the other? An example would be you use a Likert scale to test a department's feelings about a department manager's policies. A uniform distribution would be that all employees answer randomly from 1 to 5. Non-uniform would be that there's a preference toward one or more, okay? And if we look at that, another example would be you want to tell if a six-sided die is fair or not. When you roll it, you want to see, am I getting the numbers 1 through 6 relatively equally, or am I not? One more, you give a multiple choice question on a survey to see if there's a uniform response to that. They say, hey, for the next round of performance reviews, we want to know, are people more interested in seeing their insurance rates go down, their salary go up, or their vacation days go up? Something like that. Okay, so here's an example about whether a die is fair or not. So I'm going to actually grab this table and then talk it through in Excel. So if I grab that table and I dump this information into Excel, okay. So let's say I'm curious whether this information tells me if this die is fair or not. I roll the die. Okay, here are the outcomes. I could have gotten a 1, 2, 3, 4, 5, or 6. Here are the outcomes that I got. I want to see, does this data show statistically whether this is a fair die? If this were a fair die, I would expect each number to come up approximately the same amount of times as every other number. Now, that's approximately. If I roll a die, I don't expect exactly the same number to come up, but it should be close enough. And if I look at this, most of the numbers see the same, except this 2 versus the 9. I don't know on my eyeballs alone if that's statistically low enough to say, wait a second, maybe this is a weighted die and 4 never comes up or doesn't come up often enough. I don't know. And that's what statistics is for. So the first thing I'm going to do is I am going to find the sum of all these frequencies to figure out how many times I rolled the die. Okay, so I rolled the die 36 times. I am going to create a new column called expected, and this is going to be my expected frequencies based on probability alone. Well, if I roll the die 36 times and I had 6 different outcomes, I would expect 36 divided by 6. I would expect 6 times for it to come up once, and all things being equal, everything else should have come up 6 times also. So to get this expected value is your total divided by the number of outcomes. Okay? And that's how you get your expected column. If I had something like, let's say 70 different roles, over here I would do 70 divided by 6. Even if that got me a decimal, this is based on probability alone. What would you expect? All right, so if this was a perfectly fair die and everything worked out in a perfect universe, I would get 6 of each every time. So there's my given frequency. There's my expected frequency. We are going to do what's called a chi-square test. So let me insert a word box here and say, okay. So we need hypotheses. Chi-square tests have hypotheses just like everything else has had. I'm going to give you a generic hypothesis and then a more contextual hypothesis. Your generic null hypothesis for any chi-square test is going to be whether we are looking for a uniform response or not. So H sub O is the data responses are uniform, and H sub A, the data responses are not uniform. Okay. More specific hypotheses would be the data is uniform, which indicates a fair die. And H sub A, the data is not uniform, which indicates a weighted die. Okay. Our alpha level, just like before, is 0.05. I'm willing to be wrong when I run this test 5% of the time. Now, what test did we run? The nice thing is chi-square tests do not have one tail versus two tail. They just are chi-square tests, except there's technically 2 different types of chi-square tests. The one we're about to run is called a chi-square goodness of fit test. And the reason this is a goodness of fit test is I just have one set of frequencies versus some expected frequencies. Okay, I did not group my data other than I rolled a die. Okay, so this is a chi-square goodness of fit test. We're going to contrast this with a chi-square test of independence. That comes later. All right, now what we really need for this is we need a p-value. So I am going to come over here. I am going to type p-value. And I am going to get this p-value from the fx box. All right, so I am going to go into this fx box. Come here, cat. There we go. I'm going to go into this fx box and choose chi-test. All right, and my actual range is the frequencies that we were given. Stop it. There we go. Oh, everything is bad. My actual range, I have cat problems here, sorry. Let me try this one more time. Actual is right here. My expected is these things right here. And I'm going to hit OK, and I get 0.376. So my p-value is 3.376. So now I make a conclusion. Since p is not smaller than alpha, we cannot reject HO. Therefore, we retain the null hypothesis. That's not how you spell hypothesis. Hypothesis. There we go. Now, what does that mean in context? It means there is not enough evidence to reject the claim that the die is fair. That's it. That's all I can do. I can't reject the null hypothesis. So I have to say, I don't have enough evidence to say that it's not fair. So I'm just going to assume it's fair until I can prove otherwise. That's it. That's all there is to a chi-square goodness of fit test. All right, so a chi-square goodness of fit test, you go through, you figure out a frequency, and then you decide, can I tell if this is fair or not? Now, let me go back to the slides here for a moment. Okay. Okay. And we got a p-value of 0.377. Since p is greater than alpha, we do not have evidence to reject the null hypothesis. That's it. All right. Now, let's look at another set. What if I did this with a Likert survey? Okay. I want to know, based on this Likert survey, is there a response that is even? Okay, so I'm going to go back, ignore that for a second. What have I done? My computer is fritzing out. Sorry, guys. Here we go. So let's say I gave a Likert statement as part of my survey, and I want to know if there's a group response to the Likert statement. So let's come in here. I'll dump this information here. Okay. So in this, let's say I gave a Likert statement, and that Likert statement was, I can't spell today, statement. My boss is supportive of my education outside of work. Okay, so my boss supports my education. My boss supports me going out to get my degree. Okay, my boss is supportive of my education. Fine. We wrote that as a Likert statement, and then we tallied how many people said strongly agree, agree, neutral, disagree, strongly disagree. And we want to know, is there a uniform response? So it looks like I surveyed 50 people. There were 5 possible responses. So my expected frequency is 50 divided by 5, which is 10. So if there was not a group preference, there would be about 10 people in each slot. There are not. It's 15, 15, 7, 7, and 6. Is that statistically different enough from all 10s for me to say that there's a group preference? I don't know by looking at it. In chi-square tests, even for me, are something that I can't do by eyeball. I have to run it every time. Okay, so let's come down here and make hypotheses. Okay, so H sub O would be the data is uniform. H sub A, the data is not uniform, which H sub O, the uniform data does not indicate a group preference. H sub A, non-uniform data indicates a group preference. This may mean that people have bosses that do or do not support their education. So if there's a group preference here, it means that maybe there are bosses who do really support you, or alternately, do not support you. And if we look at this, it looks like 30 out of the 50 are supportive of their employees' education. So if I did indicate a group preference, I could look back at the data and say there is a group preference, and that preference is this thing. All right, alpha is 0.5. And then the test we are going to run, this is a chi-square test. And you know it's a chi-square test because we have categorical responses, levels of agreement, and we know it's a chi-square test because we're running this test based off frequencies, not numerical responses. We are running this test based on frequency values, which makes it a chi-square test. Now, this is a chi-square goodness of fit test because we are looking at one set of frequencies, okay? Now I need to get my p-value. So I am going to calculate a p-value. I am going to do that by clicking on fx again. My actual range are the frequencies I got. My expected range is this one. And I got 0.07. Pretty close, but not good enough. So our p-value is 0.077. And so our conclusion is, since p is not less than alpha, we cannot reject H sub O. Therefore, we retain the possibility that the data is uniform. Therefore, there's not a group agreement, disagreement on boss support. Now, what could you do with this information, let's say, if it was in your project? Well, if you wanted to show that your company supports your education, you would want P to be less than 0.05 because if P is less than 0.05, it means there's a group preference toward agreeing with the statement that your boss supports your education. So just because we can't reject the null hypothesis doesn't mean this isn't usable information. In fact, to me, this is very usable information because what it's showing is people are all over the map, which means if your company is trying to project that we support you going back to school, this data doesn't support that. If you were showing that your company supports your education, you should see a p-value of like 0.01 showing that there is a group preference agreeing with that support. You don't have that, which means your company isn't doing a good job of supporting you. Okay, I said the word support a lot, so hopefully that made sense. When you have a group preference, it means that you can show something specifically. When you don't have a group preference, it means that the answers are all over the map. The same could be said for those questions we had before, where if like one of your Likert statements was, the crew that came to do my lawn service was professional. If you can't show a group preference toward a response, that means you're not doing a good enough job. You definitely want people agreeing or strongly agreeing with a professional and courteous lawn crew. All right. So there is chi-square goodness of fit. Chi-square goodness of fit is when you are running stats on frequencies and you want to see if those frequencies show a group preference or not. In order to run this chi-square test and make a conclusion, you want to get a p-value. If p is small, reject the null. If p is less than 0.05, you can reject the null hypothesis, which is that there's uniform data. We never did that in any of these, but if we did reject the null hypothesis, we could support the alternative hypothesis, which indicates a group preference, and then you could run from there. Hopefully this was helpful. You will get another video soon on chi-square test of independence, and those tests of independence are a little bit different.